All right, so in this video, we're looking at the notion of arc length of a curve in space. So this is a topic that you would have seen in Calc 2 during some of the application portion of the applications of definite integrals. But here, the difference is we're looking at curves, well, in either in 2 space or in 3 space. In Calc 2, you would have only been looking at curves in the plane in 2 space. And here the formula is going to look a little different than it did there because if you're looking at a curve in 2 space, you can describe that often using an equation in the variables x and y, whereas here we're going to be working with a parameterization. And so certainly you can do the same thing in the two variable case. But here this is what we have to do. So we're going to start out with a curve C, and it's given by a parameterization R of t equals x of ti plus y of tj plus z of tk. And here our parameter t is going to run between a and b for fixed real numbers a and b. So a few quick comments. One is you notice here, and I'm following kind of the notation of our book, that for the component functions, we're going to use this x of t, y of t, and z of t rather than f, g, and h. Of course, there's no significant difference in the name of your function having a different label. You could call this whatever you want, but it does seem a little bit more, I guess, maybe match up in our minds with what's going on to actually call the component function for the I vector x of t, since I runs in the positive x direction. That seems probably a little bit easier for us to kind of remember which function corresponds to which vector if we use this choice. All right, so down here we have a picture of our curve C, just this kind of little wavy segment here. And what we're doing is we're parameterizing the points on that curve C by this position vector function. Now t here is running from a to b and not over all real numbers because we want a curve of finite lengths. Since we're interested in computing the length, if the length is infinite, then there's nothing to think about. And so what we have going on here is this first point of the curve, I have this vector from the origin to it called r of a. And then the last point of the curve, well, that gives us this vector from the origin there, which is r of b. And then every other point in the curve corresponds to r of t for some t between a and b. Okay, we're kind of familiar with this setup now. And all right, so let me give you the definition here. So the length of C is going to be defined to be this quantity down here, capital L equals the definite integral from a to b of this square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. All right, so that is the definition of the length of that curve segment. You can just sort of use it. If you see a problem on this and you have the parameterization of your curve, it's almost just an automatic thing. You just compute this quantity down here. Now, where does this come from? Maybe is a question worth asking. In fact, that is a very good question to ask. And the idea is we do the same thing we've always done in integration applications. You have the quantity you want to compute. So in this case, it'd be the length of this curve C. And you do some sort of successive approximation that gets better and better. And then the limit sort of is the thing you want. So you can imagine, let's look down here. Here's your curve C. One way you could try to approximate the length of that curve is to just take the distance in space between the two endpoints. Now, of course, that will always be an underestimate because the straightest distance is the straight line between them, and the curve, if it's straight, you'll hit it spot on, and if it's not straight, the length of the curve will actually be longer, but that'd be an approximation. It would be a pretty bad approximation in general, but a way we can get a better approximation is we could take C and we could chop it into sub pieces, and then we could approximate the length of each of those segments by actually taking the distance between the endpoints of each segment. And well, this will still be an underestimate, but it'll be a better estimate. We sum all those lengths up, and Obviously, the finer and finer we chop this thing up, the better that approximation will get. So what we can think of doing is, if our curve is parameterized as the variable t runs over a to b, we can take that interval a to b and we can subdivide it up into, in this case here, we've subdivided it into n subintervals. So here t sub 0 would correspond to a, t sub n would correspond to b, and then these are just midpoints in that interval. And the most natural thing usually would be to take subintervals of equal length. And so we could see this little segment here, for example, would be the bit we get if we take that parameterization and we just look at the subinterval t sub I minus 1 to t sub I. Now on that subinterval, the length of that piece there is approximately going to be given by the distance between this right endpoint and this left endpoint. The coordinates of the right endpoint are x of t sub I, y of t sub I, z of t sub I, and the coordinates of the left endpoint are x of t sub I minus 1, y of t sub I minus 1, and z of t sub I minus 1. Now, as you chop that thing up into finer and finer points, or into finer and finer segments, what you'll have happen is that t sub I and t sub I minus 1 will get closer and closer. In other words, these subintervals over here will be of shorter and shorter width, because the interval from a to b is some finite number, and if you chop it up into more and more pieces of equal length, the width of any one piece is going to 0. And so in the limit, that's where you're going to end up getting this x prime of t in here, y prime and z prime, because you're taking those two subinterval points and they're getting closer and closer together. And so that's where that formula basically comes from. So let's give an example here. We're going to look at this example of this curve C that's given by r of t equals cosine of ti plus sine of tj plus 2tk. This is just a portion of a helix, which we've seen that before. And what we're doing is we're sort of making, if you were staring from the top of space down onto the xy plane, you'd be making one trip around the unit circle. But again, in the z direction, we're actually rising up. And so the length, if we just go ahead and apply that formula, the length is, well, I take the derivative of cosine, which is minus sine, square that. Derivative of sine is cosine, square that. The derivative of 2t is just 2, and I square that. And then using the Pythagorean identity, I get that sine squared plus cosine squared is 1. And okay, everything else is a pretty straightforward integral. So what we find is that that curve has a length in the end here, which is 2 pi times the square root of 5 units, whatever we're measuring our length in. And what's interesting is, okay, if we were just to go around the unit circle and not be rising up in the z direction, then of course we know that we'd have done one revolution around the unit circle, and so we would have only gone a distance of 2 pi. So in this case, the fact that we were rising up in the z direction and the function that was controlling that was 2tk, it makes the length increase by this factor of square root of 5. And of course, if you have a helix that's more stretched out, then this would be even bigger. All right, another example. This was something we saw in class the other day. So this is a very easy position vector function to cook up. R of t equals ti plus t squared j plus t cubed k. And here t is going to run from 0 to 1. If you look, okay, so again, just going directly to that formula, what we find is that the length down here, okay, this is just plugging away on that formula, is given by this expression, which gives us this. Now at this point we get something that's a fairly difficult integral to compute using, trying to find an antiderivative and use the fundamental theorem of calculus. And in fact, when you're doing these arc length computations, if you could start out with a very reasonable looking position vector function in the sense that the component functions are all, like in this case, they're very friendly, right? T squared, t cubed. But when you go down and take the square root of the squares of the derivatives of the component functions, you may get something difficult, like in this case. In fact, most of the time you will. That's why we like things like the path of a helix, because you can kind of apply that Pythagorean identity to sort of simplify what's going on there with the first two components. So in any event, if you were actually computing the length of a curve in practice for some application and you needed the actual number, you would probably just figure out how many decimal places do I need to know this to, and then you could use some sort of an approximation method like we saw in Calculus 2 to do that. All right, I want to say one quick comment here. Notice that if r of t was our position vector function from earlier, then v of t, which is just the derivative of r, is what we were calling velocity, and that would look like this expression over here on the right. And we notice that those components are exactly the things that you're squaring and sticking under the square root symbol. In other words, that thing that you're integrating in the arc length definition is actually just the magnitude of the velocity vector function. So one way to sort of condense our notation, since as long as we remember what v of t is that formula we saw for arc length can be consolidated in this much tighter form. It's just the integral from a to b of the magnitude of the velocity dt. And we remember that the magnitude of the velocity is what we're calling the speed function. Now this makes sense, right? If speed is your how fast you're traveling over time, then if you integrated the speed function over time, you would have the total distance traveled. And so that should match up with what we're doing here, computing the length on this curve. All right, now we come to the arc length function. So if C is a curve parameterized by this position vector function as before, we can fix a point p sub 0 on our curve. So it's just some fixed, what we call base point, kind of a point of reference on our curve. So here it's right there. And we'll let t sub 0 be the value that our position vector function takes in to give us this point p0. What we mean by that is the vector from the origin to p0 is exactly the vector r of t sub 0. Okay. Well, at any other point, at any other value for little t that we feed into to r of t, that puts us somewhere else on this curve, and we can ask, what's the distance we've traveled along the curve to get to where r of t is putting us? Again, r of t really is the vector from the origin to a point on the curve, but using that understanding of what we mean. So obviously if t was equal to t0, then we're over here, and the distance we've traveled is nothing. And since the distance traveled is going to be, since the length is always non-negative, we're going to get a function which spits out non-negative output. And that's this function here, the arc length parameter function, s of t. So what s of t is going to do is it's the function that does exactly what I said a second ago, and we have that written sort of down here. It's going to tell you for a given t, what's the length of the portion of that curve c that goes from the point p sub 0 to the point corresponding to r of t. So what you do is, you look at this expression back up here. Little t is going to be the variable we feed into this arc length function. So you're going to integrate from t0, which is the starting t value that gets you at that base point, to this variable t here. And so now what we're going to do is we're going to compute that integral we saw a second ago for arc length, but we're going to use a different variable in here, which is the variable tau, which is the Greek letter. And the reason we're not using little t anymore is because now little t is appearing as the variable here and here. So when we integrate, we want to use a different variable for our integration, right? So imagine that as little t varies, at a given little t value, I'm integrating from t sub 0 to t, and so I'm going to use a different variable to feed into v that will range from those values. And so that's where the tau comes in. Notice then, by the fundamental theorem of calculus, that we have, let's scroll up here, that we have the derivative of the arc length function. If you remember how the fundamental theorem of calculus looks, it's exactly now going to be the magnitude of v of t, in other words, the speed function. But again, this makes sense, right? Change in length with respect to time should equal speed. Remember, speed is just a non-negative number that's telling you how fast you're moving. Velocity is tracking speed and direction you're heading. But speed is just that magnitude portion of velocity. So this actually makes sense when you sit there and think about it. All right, the last thing for this video is just quickly, I had made this comment last week. When you have a velocity vector, it's what I just said a second ago. It's got direction, it's got magnitude. The direction portion of the velocity vector is what you get when you take the velocity vector and you just divide out the magnitude part of it, so the speed. And now we give that a special name and we call that the unit tangent vector function, and it's denoted by this capital T with a vector arrow over it. So it's a function, and all it's doing is it's spitting out a unit vector that points in the direction of the velocity vector. So in general, the velocity vector will be longer than unit length because it will be carrying with it how fast your particle is traveling. But here, this is sort of a just a portion of essentially of the velocity that's only tracking the direction it's heading at a given time.